and he is going to tell us about upgrading biochar into activated carbon materials through physical activation.
So if it's all right, I'm going to stand over here. That way I can see everyone's pretty face. So briefly, I'm going to introduce pretty much what we already have been talking about all day: pyrolysis, thermochemical conversion of biomass, some of the materials and methods that I've been using to upgrade the biochar into activated carbon, the experiments, results, and conclusion based from those. So why do we want to look at biochar? Well, originally there's a high demand for alternative energy, and it doesn't seem to be decreasing in the near future. We want to reduce our greenhouse gases, and we want to have clean, renewable biofuels. Unlike ethanol and biodiesel, which can only be added to traditional transportation vehicles, future second-generation technologies utilizing thermochemical conversion can actually produce gasoline, diesel, jet fuel at much higher drop-in rates for drop-in fuels for traditional vehicles. And it can utilize a lot of inedible lignocellulosic biomass, so we don't have to compete for soybeans or corn based on first-generation biofuels. Just like before, it's the fast pyrolysis is typically the thermal decomposition at high temperatures in the absence of oxygen. It can use a variety of biomass feedstocks and typically yields around 50 to 70 weight% of bio-oil, which is a liquid precursor to the drop-in fuels. The reason why most of the thermochemical conversion is focused on the bio-oil and kind of neglects the byproducts for biochar and synthesis gas, they're typically much less yield. So syngas is around 15 to 20% based on the process, and it has a composition of CO2, CO, hydrogen, and methane are the predominant components. It's actually a majority of CO2 and carbon monoxide in fast pyrolysis. And so the proposed uses would be for Fischer-Tropsch synthesis, or it could be also burned for additional process heat. But since you're not usually producing a majority focused into syngas, traditional fast pyrolysis processes look at burning it for process heat. Biochar also has 10 to 30 weight% yield, and it's mainly carbon that we've all seen prior to today, and it also has an amount of ash. Based on the process, the amount of ash, and based on the biomass feedstock, the ash could vary from 1%, 5% to above 10%. And we've talked a lot about the proposed uses for soil amendment, carbon sequestration, and also for some thermochemical processes, they plan on burning it for additional process heat. Since fast pyrolysis is actually endothermic and requires energy to break down and thermally decompose the biomass to produce the bio-oil. So here's the typical fast pyrolysis system. You can see that biomass would go into the reactor. You'd have a condenser system to obtain your bio-oil. Syngas and biochar could go to the combustion system to bring back process heat for your reactor. So for our project, we actually want to take this biochar and upgrade it into activated carbon because another high-value added co-product would help improve the overall economic platform for thermochemical biofuels. Right now, they've been having a techno-economic analysis, and they have, I believe it's around $2 of per gallon of energy equivalent for bio-oil as the liquid precursor for the fuels. So that kind of needs to bring the cost down in order to make it more viable going forward. We want to use different activation methods, physical or chemical activation, where you would have a partially oxidative reactant come in and develop macropores, mesopores, and micropores. And ideally, you'd want to just react with the carbon matrix to develop porosity and increase the overall surface area. And for this experiment, we're going to be using flue gas components, CO2 and H2O, individually, together, and then also fast pyrolysis syngas. So why do we want activated carbon? It's used primarily for potable water treatment to purify water. And in the increasing global population in developing countries is increasing demand for clean water. Also here in the US, new EPA emissions are requiring coal-fired power plants to reduce the emissions and the particulates that are being released from these coal-powered incinerators and boilers. And based on a market analysis by marketsandmarkets.com for activated carbon, there's a global annual growth rate of 11.1% from 2011 to 2016, which we're currently in the middle of. So not only is we're taking biochar, which there's a very small market, not necessarily a large global market, there already is one for activated carbon, and it's growing right now. So for the experiments, I used a fixed bed reactor where we can adjust the temperature within the furnace. We can also have a gas inlet below the biochar, which is placed in a stainless steel mesh basket, and then the exhaust gases can be easily removed. For analysis of our activated carbon, we use a Micromeritics TriStar 3000. We could test 3 samples at a time for quick screening of our materials. And we primarily measure the BET surface area. So when the sample is being analyzed, it's at very low pressure under vacuum, and it slowly will dose it with additional nitrogen. And as the nitrogen is increased, it'll start to form this monolayer of nitrogen molecules that are physically absorbed to the surface. And since we know the size of a nitrogen molecule, we can calculate the BET surface area of that monolayer. And when you increase the pressure to its full saturation, you can measure the total pore volume. And when you decrease the pressure back, you can get this hysteresis loop, so you could get the pore characteristics, basically the shape of the pores in the carbon matrix. For the CO2 experiments, it's primarily focused on the Boudard reaction. The gaseous CO2 will react with the solid carbon and form 2 moles of carbon monoxide. For our experiments, we need to run at very high temperature. So looking at the thermodynamics, at low temperatures, CO2 is the favored product. But then above 675 degrees C, CO becomes more favorable, and the reaction is proceeding. It's interesting, though, that our reactant will also be our product. So we want to be able to adjust and analyze, well, between 800, 850, 900 degrees C, we can get very good reactivity, but we also want to retain that carbon for activated carbon production. So here's the results of using CO2 at 0.7 liters per minute flow rate. And at different temperatures, you could see the starting biochar surface area of around 262 square meters per gram. And at different times, a larger amount of carbon is being converted to form this carbon monoxide as the reaction progresses. And taking this further, even though you can produce a very good activated carbon above 1,400 square meters per gram, the yield that you would get isn't ideal for a production standpoint. And you would really need to see at what amount of conversion can you produce a profitable amount of activated carbon. So going forward, I'm going to take the surface area and multiply it by the yield and have the same x-axis. And when we take a look at that, you can see that even though you have very good surface area, you're just not making enough. And around 40% is where the optimum amount would be, where you have a pretty good activated carbon that's being produced, but you have an abundant amount of it for selling. So we wanted to analyze the effect of temperature and flow rate. And the blue represents 1.3 liters per minute of CO2 all the way down to 0.4 liters per minute. So we can see that at 900 degrees C, that trendline peak is actually the highest for 900 degrees C at all flow rates. And then within this temperature, the lowest flow rate produces the highest trendline peak. So you want the high temperature to be very reactive for the carbon to react with CO2. And then you also want a very low flow rate. What's happening is you're creating these pores, and then when there's an abundant amount of CO2 around the surface, you're going to be destroying the pores as well. So you want a fine balance of pore creation versus pore destruction. So going forward, we also want to look at steam experiments using, instead of CO2, the other flue gas component of water. And if we just take water and react it with carbon, we're going to have carbon monoxide and hydrogen. What's happening, though, is within the pore, 2 moles of hydrogen can further react with carbon and produce methane. And then the water and carbon monoxide that's produced from the first reaction can undergo water gas shift and produce more CO2. And just like before, the CO2 can react with carbon and make 2 moles of carbon monoxide. So steam is actually more reactive, and when it diffuses into the pores, it'll continue to react from the other byproducts of the reactions. And typically you'll get bigger pores as the activation reaction progresses. So here's another plot. Before we were around 1400, we can easily get above 1500 and 1600. And when we take a look at the BET surface area times yield and compare that to the burn-off, it's just like before. Around 40%, we reach our maximum peak, and 900 degrees C is very reactive as well. We reduce the flow rate from 1 milliliter per minute to 0.33 milliliters per minute, and we see the same trend. At 900 degrees C, we reach a higher trendline peak, and at lower flow rate, we have a higher trendline peak. When we compare everything at 900 degrees C, since it's the best reaction temperature, we can see that for CO2, we're getting around 500, a little bit below, a little bit above. For the water, there's a drastic increase with 0.33 milliliters per minute. And this is a combination of CO2 and water together, an equal molar concentration of activating agent, where it's 0.4 liters per minute of CO2 with 0.33 milliliters per minute of water. And this we can obtain the trendline peak around 575. And this is the carbon BET surface area times yield percentage. Going forward, we wanted to also look at syngas experiments. So these are the typical syngas products from a fast pyrolysis system from the National Renewable Energy Lab 2010 technical report. And as you can see, carbon dioxide and carbon monoxide are the predominant products that are produced. Methane, ethane, hydrogen. Hydrogen is the next largest one, along with propane and ammonia. So CO2 and CO account for almost 93%. And going forward, when I say syngas experiments, I focused on just using these 2 gas to have more of a model control over our experiments. And since CO wouldn't really react with the carbon, it's going to be the same as the Boudard reaction using the CO2. So we can see with the syngas activation going forward, it's the same, taking the biochar initial surface area, and we can increase it dramatically. And the syngas activation will get around 600 carbon BET surface area times yield percentage. Comparing that to everything else before at 900 degrees C, we can see that syngas produces the best as of right now. And this is using 0.4 liters per minute of carbon dioxide and 0.5 liters per minute of carbon monoxide, the actual ratio that's similar to fast pyrolysis composition. And this is the same amount of moles of CO2 just like before. So it's directly comparable experiments. We want to know, why is syngas so effective? So when we take a look at the Langmuir kinetic mechanism, we have carbon dioxide right here, and one oxygen will be reacting with the carbon that's on the surface of biochar. When it does, we have a CO blockage of a carbon active site, and it prevents further CO2 from reacting where that would be. And then once the carbon monoxide will desorb, we have development of further porosity. So it's going back to the beginning where we want the reaction to proceed and we want to generate CO, but we don't want to do it too much and too quickly where it will actually destroy the pores. We want to create more pores and higher surface area. So our proposed integration of using this would be you have your original biomass, you have your condenser system to make the bio-oil. You have the syngas, which would be first burnt or, to supply process heat. But then you could use the syngas and react it with the biochar in a secondary reactor at an elevated temperature around 900 degrees C. You can have an improved syngas with higher carbon monoxide concentration. You can get additional process heat. You can have activated carbon that's produced as a result of your whole process. And you would actually have, you'd have the hydrocarbons in the bio-oil to be used for biofuels. You'd have activated carbon that would be typically worth a little bit more than biochar. And you would have even more syngas that's being turned in for process heat. So you have an overall better utilization of carbon from the original biomass feedstock. So our conclusion is that physical activation effectively increased the surface area of the starting biochar. Lower flow rates and higher temperature create higher surface area due to the balance of pore creation versus pore destruction, and that fast pyrolysis syngas does develop the best activated carbon on a surface area times yield basis, and that you could produce a maximum amount of activated carbon at around 40% conversion. For future work, we're planning to use a new reactor with a rotary furnace. Instead of a fixed bed where the biochar is stationary, if you have a rotary bed, you can actually get better interaction between the gas and the carbon and have better turnover, and you can have just a better mixture of both reactants. We like to try different types of biochar. The biochar that we used was a commercial biochar provided by ICM Incorporated, and they primarily focus on thermochemical gasification processes. And we would like to go back and take a look at that techno-economic analysis and try to detail our proposed integration compared to their traditional scope. So I'd like to acknowledge our funding agency, the USDA, and all other members of Dr. Gu's research team. Hong Jin, who you already saw before if you were here, Wang Xiaoming, and Sahan Li. Thank you very much.
Any questions?
Yep.
I had a question regarding rates. The fast pyrolysis, very quick
Yep.
rates. Now you're going to go and you're going to combine the two. You're going to take the biochar and the syngas. What's the residence time in that?
So around that 40% conversion was around 10 to 20 minutes reaction time, because you do want to activate it slowly. Also, since you're using fast pyrolysis and you would have an abundance of biochar coming in, that would typically take place at around 600 degrees C, so you would need to ramp up to a 900 degrees C reactor, secondary reactor, for activation.
Biochar is moving from the reactor to another activation reactor.
Yep. That's what our proposed integration would be. Yep.
Are you familiar with the pyrolysis platform and activation method that the Forest Products Research Lab in Wisconsin, and are you on a parallel path with them?
I'm not too familiar. All right. Oh, all right. Excellent. Yes.
You use a couple of reactions to upgrade the biochar, right?
Mm-hmm.
And why do you call it as your approach as physical activation? Actually, it's still kind of chemical activation.
Chemical activation would be using sodium hydroxide or potassium hydroxide, and taking an aqueous solution with that and impregnating the biochar directly, and then would be placing it into the furnace and doing your reactions at high temperature. So it's, yes, I know there's chemistry involved, but it's more of a physical phenomenon of taking a vapor and reacting with the solid biochar. It's actually woody biomass that they used for ICM Incorporated for their gasification. Yeah, mixed wood. Yep. Yeah, they basically gave us a couple pallets of woody, woody biomass biochar that they produced, and they have so much that.
I can answer this question better. We have the renewable kinds of biochar from the industry guys and also the forest service in the Wisconsin. Dr. Anderson, Nick. Yeah, Nick Anderson. He sent me several biochar from his project, the bird project. We talked each other just last week. Looked like interesting. Some biochar after the high temperature pyrolysis, he used the 1,000 degree to do the pyrolysis either. Those kind of biochar after the activation give a really interesting result for the surface area. And the column also show the structure very graphite. But some biochar from honeydew, beetle killed the trees, a little bit different. But the general case, we will get the surface area around like 700 to the 1,000, just like that.
So taking your original biochar and react 40%, so you have a 60% yield of activated carbon from that secondary reactor system. Because you'd want to produce the most amount of activated carbon to offset other additional operating costs for producing your bio-oil. Yep.
What is the syngas composition after biochar activation?
Well, it would be more increased in CO production because the carbon dioxide would be reacting with 1 mole of carbon in the biochar to produce 2 moles of carbon monoxide.
Any change in the hydrogen composition?
See, we didn't use hydrogen. We just stuck with the highest percentage, which was 93% of the overall composition. In the future work, we probably would like to use direct syngas from a fast pyrolysis reactor to see how it would be better for scaling up. Because like the steam, the several pathways, the hydrogen would further react. So I expect it would increase the surface area as well.
So the ones that you presented in this work is synthetic syngas?
Yes, model components.
Thanks, Joe.
Thank you.